Hey guys, one of the things that's valuable, I just mentioned this to Jeff, we haven't said it for a while, but as you're going in the direction of engineering, certainly, a reminder, if you go to Portland State, the end of their Portland State, they waive a lot of the physics prerequisites for their degree requirements in lieu of the engineering requirements for electrical, civil, and mechanical. Because you take thermodynamics, you take these high-level mechanics classes, hydrodynamics, etc. So what ends up happening is a double major in physics and engineering boils down to taking the year of modern physics. And I don't even think you need the modern physics lab, you might. And one term of optics. That's not bad for a double major.
Years.
It ends up being an extra year. Most engineers spread out their engineering work over 5 years or 3 years. Their 2-year junior senior classes typically are spread out over 3 years anyway. So adding that one extra class here and there doesn't really amount to much. Because you don't want to be taking 17, 18 credits of engineering classes a quarter anyway. And the thing about physics is while it may be technical, the workload as far as the assignments is much lower because physicists don't require the type of busy work. You know, the 15 problems, each of which require 2 pages. So, to that end, it makes life a little bit simpler. Okay, so let's add to this then the next piece of the puzzle. And this is now, believe it or not, we can establish 2 fundamental laws of electromagnetism right now. This is beautiful if you think about it. First of all, Gauss's law. Gauss's law establishes something about the nature of electric charge and electric fields, right? And the idea is electric flux, which corresponds to calculating over a closed surface. Sorry about this pen here, I'll change. Related to the Q enclosed over epsilon naught. Okay? Now here's what's interesting. The assumption of this is that you take a closed surface and you isolate a net quantity of charge inside. But you can't do that with magnetism. We've never actually seen a point magnetic charge. Even with an individual charge in movement, there's always a simultaneous correspondence to north and south. You can never split a bar magnet into a north piece and a south piece. Which means that if you apply Gauss's law for magnetism, by looking over a closed space and measuring dA, or BdA over a closed space, if you were to set that equal to a point magnetic charge, doesn't exist. This actually works out to 0. Believe it or not, this is a fundamental analog for magnetic fields to this. Now, we didn't really talk about it, but it is, and it's just because there's no such thing as a point charge. So no matter how you try to collect a surface and put it around a magnetic field or a magnetic source, you'd never get a net magnetic monopole, if you will, or magnetic point charge. You're always going to have an equal N and S, north and south. So this quantity just works out to 0. And remember, it's about fields and their source. Fields and their source. Fields and their source. So there's nothing fancy here. But this is the second of Gauss's law. Or, the second interpretation of Gauss's law. Turns out there's only 2 other interactions that describe everything. Only 2, which is freaky if you think about it. The next one is one we're going to talk about, which is called Ampere's law. And at some point, shortly, hopefully by Tuesday, or maybe even on Friday's lab, we'll talk about Faraday's law. Now here's the thing about Ampere's law, and there's a lot of finagling and there's a lot of little pieces. But think about this for a second. Instead of a charge of Q, what if you have a moving charge or a flow of charge dq dt? Gauss's law would look a little bit different, wouldn't it? There's a lot of vector identities built into this, at least in terms of interpretation, so I can only take it so far. But if we know that the time derivative of Gauss's law would look something like this. Take a closed surface, a Gaussian surface, and you have a flow of charge going into it, dq dt. So basically, you've just got charge flowing into some surface and doesn't come back out, or you have a net charge flowing in that's greater. Whatever charge flowing out is less than what's going in, or more, as long as there's an imbalance. So maybe we call this dq in and dq out, dq dt, so that dq enclosed at any given time, dq net, would be the difference between dq in dt minus dq out dt. This is enclosed, sorry. Nothing fancy, I'm just saying, if you looked at this possibility, and again, this is just a closed Gaussian surface. Then if you looked at Gauss's law under these conditions, or if you just basically extended that, then what ought to have happened is that dq enclosed, dt, divided by epsilon naught, should be equal to d flux dt, right? The area stays the same, and the only thing that's changing, well, it doesn't matter if the area is staying the same or changing. If this is changing with time, this will change with time. Which is another way of saying d dt, d dA. Now, we could write I or dq enclosed dt as basically the I, if you will, not enclosed, but the I flowing in or out, the net I, if you will, over epsilon naught. And that ought to be equal, if the area stays the same, we're looking at the same area that we're integrating over, then this implies this. Very simple. Now, what do we know about EDT? What does EDT imply? When you have a changing electric field, what does that imply that might be happening simultaneously?
Magnetic field.
A magnetic field. So I'm not, there's a little bit more finagling that goes in here, and I'm going to just kind of cut to the chase. But I want to just point out that just the time change of Gauss's law implies something about the relationship I don't know what form it takes, but there's going to have something about B built into DA. I'm putting a question mark there because I'm not going to state directly here what it is. There's a little bit of vector manipulation that gets involved. But if you sort of see this, it sort of tells you something interesting. It tells you would expect, just on the virtue of Gauss's law, that if it changes with time, as charge changes with time over some defined area, you would expect an associated magnetic field, and you would expect, under certain conditions, maybe to be able to solve it, and also that the magnetic field will somehow correspond to that flow of current. Well, you manipulate this enough, and if you've taken vector calculus, you'll see that there's a way of interpreting integrals as derivative forms. You use the del function. There's some things built in there. But what this will reduce to, if you look at, now you got to take by faith, is something that's quite nefarious, or quite, I shouldn't say nefarious, quite interesting. If we reduce this Gaussian surface to basically, right, it's a sphere, I'm just going to reduce it to basically a slice in space. So I'm just going to shrink this Gaussian sphere to the point that it's basically just a little tiny little cylinder, or a line, a patch, if you will, in space, where this current, this dq dt, is flowing through it. Well, as it flows through this thing, I'm going to say here's the breaking point, where the current's flowing across this little patch. Here's what's kind of interesting about it. It turns out that if you were to calculate, and we know something about the magnetic field, right? If you have a line of charge, the direction of the magnetic field, or the line of a wire of current, the direction of the magnetic field will circulate around the perimeter at a distance r, around the circumference at any particular distance r around this wire, perpendicular to the plane of the movement of the wire, and also to the distance of separation vector. It turns out that if you looked at every tiny point here, and this is, you have to take this a little bit on faith, because it's, if I looked at a little segment d, let's call it dl, and all dl is now is a little segment along the circumference of this ring. And by the way, this is a 90-degree angle between the current as it comes out and this surface. Right? So basically it's a circle and a line and a current wire going through it. If you add up all of these little, and there's a magnetic field there, right? In this little region, at a particular distance away, in D, or along DL, I should say, you can calculate the quantity B, DL, because B is going to be along the direction of that path. And so you can look at the field pointing along that path, kind of like the velocity, instantaneous velocity along a uniform circular path. If here's your DL, your B is pointing this way, and your DL at that particular point is also pointing that way. If you calculate the sum of all of those BDLs, and there's some vector stuff going in here, along the whole path, which you could think of as some path basically drawn at some point along the perimeter of a Gaussian sphere, if you will, or along any Gaussian closed surface. Turns out that this quantity will always equal mu naught times the amount of current that flows through the normal, if you will, to that closed surface. Kind of like Gauss's law, I got no justification for this. There are ways of looking at different experiments and reducing it, and it always works out to the equivalent of this. Okay? But this is Gauss's law, or this is Gauss's equivalent law for magnetic field. Now it's no longer a closed Gaussian surface, now it's a closed path. And we call it a closed Amperian path. I know, just change the names, right? But it turns out, for any closed path, start and end up at the same point. The quantity, the sum of all of the dot products of B and the path segment that's oriented along or with that magnetic field. If you add them all up from any closed surface, it will always correspond to the amount of current flowing through times some constant. May or may not seem obvious, but it doesn't matter what type of surface you put a current through it, it's always going to work out to that relationship. It's a fundamental law in nature. And its path integral, there's no special name for it, at least I don't know if there's a special name for it. But ultimately, we can add this to our toolbar, or to our toolbox, of relationships to make certain calculations. So, on the surface, it is what it is, right? Take some closed sausage-looking surface and stick it around a point charge, and always calculate the flux is equal to Q inside over epsilon naught. Maybe not useful, but it will always be. Okay? It's one of those phenomena in nature. On the other hand, in some cases, this makes calculating B a hell of a lot easier than using that expression, that Coulomb law interpretation of magnetic field, which is referred to as Biot-Savart relationship. Savart, how you pronounce it in French. So, this is where physicists appreciate this, even physics students appreciate this more than engineering students or biologists, but ultimately, this is a tool with symmetry used to calculate magnetic fields. And that's what we'll use it for. It makes life a hell of a lot easier when we use that. And the trick is just like Gauss's law. So, I take a wire with a current I flowing through that wire. And I want to know, what is the magnetic field out here somewhere? At point P, what is B? Now, this is where maybe the massage or the zen of it comes in. But, okay, I want to pick a path so that I can calculate B multiplied by dl, scalar product of B dl. But it's only going to be useful if I do this calculation over some length of some path, some combined path. It's only going to be useful if B is either 0 somewhere or B is a constant. If B is not a constant or B is not 0 along dl, along this vector segment, it's not useful at all. It's only useful when it is. Okay? So I'm going to note this. If I were to draw a cylinder. If I were to draw a circle centered on the wire, where the wire is normal, the face of the wire is normal to the wire. Then every segment of BDL will have the same orientation of B, because we've already established that B by the right-hand rule should sort of form and follow a certain direction around the wire. All of these segments will have the same orientation of and quantity of B. So B will be constant along every DL segment, very important, and oriented in the same way. If you will, parallel to DL. So the way we would apply the problem, then, to apply Ampere's law, we've started by figuring out a useful path. First thing, we need a useful path. And these are the requirements for that path, usually. Once we establish that useful path, then we integrate BDL along that path. And B dot DL as vectors reduces to BDL in the parallel. In this case, it just reduces to this. And this will correspond to mu naught times the amount of current in that wire that's passing through. Now over this closed path then, B comes out, because B is constant with respect to DL, and I'm left with DL around this circle. Which, if I really wanted to be special about it, I could say, well, that circle would have a value of R d theta over every tiny little segment theta, if you will. So this is DL, and this is R at this distance. The magnitude of DL should be R d theta. What's that? So now we're left with integrating R d theta over a constant R, going all the way around the circle from 0 to 2 pi. Or if you will, B times 2 pi R is the total path, and B is uniform, at least in terms of magnitude and orientation, along that path at every point along that circumference. And this will be equal to mu naught I. Of course, I'm getting simpler than that. It's weird to think about, but the mechanics are fairly straightforward.
Well, that's the same thing as we just did before the break.
What's that?
It's the same thing as we just did before the break, only now the 2 pi r is on the other side of the equation.
You betcha. So if we solve for B, then, at any position P, if you will, it's going to have a magnitude of mu naught I divided by 2 pi r. And the direction, based on the right-hand rule. So I'll use a different color here just to indicate if we wanted to get the direction out of it, we'll just get the direction by the right-hand rule. So, to this end, for a current flowing in of 1 ampere, at a distance, r is equal to, say, 0.05 meters. B reduces to mu naught times 1 ampere divided by 2 pi times 0.05 meters, which ends up looking like 2 times 10 to the negative 7, 2 times 10 to the negative 5th divided by 5, so 4 times 10 to the negative 6. We just saw that before.
Glad to see you last night.
Oh, no worries. The direction would be according to the right-hand rule, depending on where exactly you were around it. That's kind of cool. So everything we did in that long integral calculation actually reduces in a simple form to this. Now,
The wire has to be long compared to R for this, for us to use this Gaussian.
absolutely.
Or
Let's
that
think about the
period.
limitations. If you're not centered on the wire, okay, there's a subtlety here that is maybe not obvious. If you're not centered on the wire, then B dl may not necessarily be a constant quantity. It may not be oriented in the same direction. So fundamentally, it's a correct assumption, but the VDL quantity being mu naught I enclosed may not be as obvious in terms of application as it should be. So even for a uniform distance, so you got to be a little bit careful, but this relationship is absolutely valid in all cases. What's that? R would be just whatever this distance was. So what did I use? I said for R of 5 centimeters, just to use a problem that we used before. And the point of it is that it reduces directly to the calculations we're using with our Coulomb analog. So that's basically the idea. It's pretty straightforward. It's pretty easy to use, but it's only useful in a couple different configurations. Another example where it's useful, and I think this is about the last one I can think of off the top of my head. No, I guess I could think of a couple of them. None of them are particularly helpful. But very briefly, what if I had a solenoid of uniform coil segments, uniform coil spacing, with a current running through it? So it could be a toroid too, but let's just look at a straight solenoid with uniform coil spacing. So nothing fancy, just uniform, so we don't have funky calculations to do. So the idea would be something like this. So it's going into the table, it's coming out, something like this. So I've got some N coils. Over the length of the solenoid L. The question then becomes, well, and so here's my little wire. So the current's flowing in this way. And so at every point, the current is going to flow as it gets along the outer edge like this. On the outside and then out this way. So how do we apply Ampere's law to solve this problem? Solving it with the BS4 would be hellacious, because you'd have to pick some point in here and then define every segment ds and its relationship to the center of that solenoid, if you will. My God, that's a nasty calculation. But look about this. What type of an orientation could we use that would be helpful for Ampere's law? If I drew a segment this way through the center, BDL, if I know ahead of time that it's a constant current or a constant magnetic field inside, and I go right down the center, then B and DL going from one end to the other is going to be a constant quantity. Now, here's where you get tricky, and it's all these mathematical little screwy things, and they're hard for a realist, kinesthetic rationalist to fully appreciate, no doubt about it. But what if I drew and made this into a rectangle that was a 90-degree angle with a segment that is relatively far away from the solenoid? BDL will be constant up here. But the magnitude of B with respect to down here is going to be as long as it's tiny compared to that, and it won't be compacted in that tiny little space, so it will be, with very little effort, putting it up here somewhere. And along the sides, my DL and my B won't have value. Let's do it this way. So I'm going to draw my path like this. Now if my field's running this way in here, it's going to run parallel on the outside. And even on the inside, it's going to be 90 degrees with respect to the path. So I'm going to have a BDL along these surfaces of 0, or along the sides of 0. And I'm going to have a BDL that is negligibly small along that top portion. So if you apply Gauss's law, or Ampere's law to this, then we would say the integral of B dl over this entire path really corresponds to B inside times some length here, I'll just call it L, plus 0, maybe we'll call this L inside,